Hey, welcome back to Calculus. This is still from section 5.3. I just want to do another example where we compute a definite integral by taking limits of Riemann sums. The main video lecture for this section just had one computation worked out. I'm going to write this one out as we go to give you some more experience in doing these things yourself. So the integral that I want to compute, you can see it here. It's the integral from 1 to 3 of the linear function 3x plus 7. And before we do it, we can even kind of visualize what we're doing geometrically here. I won't have a fancy computer-generated image, but 3x plus 7 is just a linear function. So if I don't worry about drawing this picture to scale, its positive slope has a positive y-intercept. So let's say that that function maybe looks like this. Yeah. So there's our function y equals 3x plus 7. And again, this is just schematic. Let's say that maybe x equals 1 is right here, and x equals 3 is right here. So this integral represents the area of this region R that's bounded by that curve. Yeah, that region has straight sides, so we can figure out the area of that with a geometry formula. Yeah, it's the area of a trapezoid. To know the area of a trapezoid, you take the average of its sort of base lengths, if you like, and then you multiply that average by its height, which in this case is going to be 3 minus 1. Okay, so let's work out that. What are those base lengths? If x is 1, 3x plus 7 is equal to 10. So that's the point 1 comma 10 right there. And if x is 3, 3 times 3 is 9, plus 7, 16. So that's the point 3 comma 16. So the area of this region R, by that formula for the area of a trapezoid, it should be 1/2 the sum of the base lengths, so that's 10 plus 16. And then we multiply that by our 3 minus 1, our kind of height of the trapezoid, if you like, or width, more like in the picture that we're looking at. So what is that? 10 plus 16 is 26. You divide that by 2, that's 13. 13 times 2 again is back to 26. So the answer that we should get is 26 square units of area. Okay, so let's see if we can confirm this with the integral. Okay, we're going to see if we can confirm this with the integral. I'm going to take the limit of this thing, the limit of its Riemann sums. So let's copy the integral that we're talking about and drag it down here where we have some room to work. And we'll start making that computation. So the first thing I want to do is compute my step size. My step size is always the width of the interval. That's our 3 minus 1 over n. N stays as a variable. It's the number of rectangles that we're eventually going to let go to infinity. So in this case, our step size is 2 over n. And then the ith endpoint. The ith endpoint is always the leftmost endpoint. That's the lower limit of integration 1 plus I times that step size. Okay, simplifying that a little bit, that's 1 plus 2I over n, and that's valid for I equaling 1 to n. Those are the values I'm going to use. It's valid for I equals 0 as well. But these are our right-hand endpoints. These are the values of I I'm going to use in our sum. Okay, so now we write the definition. This integral, the integral from 1 to 3 of 3x plus 7, is by definition the limit as n goes to infinity of the sum as I goes from 1 to n of the function's value f of xi times our delta x. Okay, and if it's not clear here, my f of x in this particular problem is our 3x plus 7. All right, so what I've written right here is the generic right-hand endpoint Riemann sum for any integral, but now we have to put in the information from this example. So again, notice I'm going to keep writing the limit. I'm going to keep keeping my information organized, the sum. It's okay, just take time and do it. What is f of xi? Well, I've got xi written right up here. It's 1 plus 2I over n. And where does the input go in our function? Just in one spot. It needs to go in for right there. So I need to take 3 and multiply it by the quantity 1 plus 2I over n, and then add 7 to that. And that whole quantity has to get multiplied by my delta x, that's my 2 over n. So these parentheses I just made were necessary because otherwise I would just multiply the 7 by 2 over n and not the first part. So you have to treat quantities appropriately with your algebra. And now the next line, actually, maybe I should just be quiet because I just need to algebraically manipulate this thing until I can use those formulas from Appendix E to write these sums as functions of n. So a lot of copying here, but it's good to use the notation carefully. So let me first distribute that 3 in there. So I'm going to get 3 times 1 and 3 times 2i over n. Well, let me not skip any steps. So I have 3 plus 6i over n plus 7 in those parentheses. That all needs to get multiplied by 2 over n. So continuing, got my limit of my sum. I goes from 1 to n. Well, 3 plus 7 is 10. And if I multiply 10 by 2 over n, I get 20 over n. And then if I multiply 6i over n by 2 over n, I get 12i over n squared. Okay, now we're kind of in familiar looking territory. That's the limit as n goes to infinity. I'm going to split this into two sums, I equaling 1 to n of 20 over n, plus the sum as I goes from 1 to n of 12i over n squared. So I'm taking the limit of those two things. I'll put the brackets to clarify that. Okay. Still writing my limit, haven't taken it yet. 20 over n doesn't depend on I, so it can come through that sum. So I have the sum as I goes from 1 to n of just 1. Likewise, 12 over n squared doesn't depend on I. So out it goes. That's I equal 1 to n of just I. All right, and now you see, I'll write them in a different color. The brackets, these expressions, the sum as I goes from 1 to n of 1, and the sum as I goes from 1 to n of I, those are the formulas that we developed back in Appendix E. Yeah, so I'm just going to substitute in their values. Still haven't taken the limit. So I have 20 over n. Well, the sum as I goes from 1 to n of 1 is just n. And then I've got 12 over n squared. The sum as I goes from 1 to n of I is our n times n plus 1 over 2. So those are formulas from Appendix E. And now we're just about ready to take this limit. 20 over n times n is just 20. And what would we get here? Well, we'd get, you can multiply it out if you want, but it's 12 times n squared plus n over 2n squared. All right, so what is that limit? Well, the limit as n goes to infinity of 20 is 20. And here in the numerator, your degree 2 polynomial has coefficient 12. In the denominator, it's degree 2. It has coefficient 2. So that limit is their ratio, 12 over 2. So that's 20 plus 6. Well, there you go, 26 square units. So there is our second example of computing a definite integral by taking limits of Riemann sums. And I hope that it's helping you get the hang of the kinds of algebra and limit manipulations that you have to do, as well as using those facts from Appendix E on summation. All right, so the same technique can handle any f of x up to a cubic polynomial. So in the lecture, I did a quadratic. Now I've done a linear. Maybe I'll make one more video in which we can try to tackle a cubic polynomial together. Okay, thanks for listening.